Hello Internet, my name is Quinn and this is Blondihacks. I'm back on the Pennsylvania A3 switcher locomotive build this week. This is kind of a big day because I'm going to start officially on the running gear, which I know is the part of this locomotive that most of you are probably the most interested in. We're going to start with the front axle box, which is quite a complex single component, so we're going to devote this entire episode to it. This is really the bridge between the suspension and the bearing carriers. It really ties everything all together. So it's a lot of neat operations in this, I think. I hope you enjoy it. Let's go. We're steaming along on this locomotive chassis. This hole here is for the front axle box. That's what we're building today. I've got this big piece of brass. We're going to machine this whole assembly out of a single piece. I bought an oversized piece so that we can machine every surface as accurately as possible, because we do have a lot of precision that we need to hit for this part. I don't want to rely on any factory surfaces this time around. For most parts, the factory surfaces are fine in many cases, but not this time. I'm going to rough cut that to length on ye olde bandsaw and over to the milling machine to bring this down to the outer dimensions of the overall assembly. I'm going to try to save some time by using my Shrum Solutions Tri-Fly. This is a small insert face mill designed for small milling machines. You know, the big insert face mills that you see the big kids use, you can't use on small machines like these. Really long-time viewers will know that I used to use shell mills for this, which are kind of like a really big end mill with a hollow center. And they also act like a small facing mill, but they do wear out and then they're really difficult to regrind. Unfortunately, this time that is a terrible job. In fact, that surface finish is awful. I think I've got the wrong inserts in this thing for brass. The corners are also probably toast on it, so I could rotate them, but I know for a fact that it's the wrong insert for brass anyway, so why bother? I dug through my bins and I've been donated a lot of inserts over the years from various viewers, even though I don't use a lot of insert cutters here. But I have these ones here, which are spec'd for aluminum, and they work super well on brass as well, especially on small machine tools. Please don't ask me what the number is or for a link to these inserts. I can't tell you. They were donated. They came in a blue box. That's all I know. However, you can tell from looking at them, they have a very sharp edge and a very high top rake on them, which means they're designed for aluminum. They're also uncoated, which is typical of aluminum inserts. I think it was my friend James Clow who first put me on to using aluminum spec'd inserts on small machine tools. Because they're so sharp, because that's what aluminum wants, they really act like high-speed steel. And they have very low tool pressure, and they do a beautiful job on honestly all materials. This finish now is so good that honestly I can't even see tool marks in that, which is pretty remarkable. I use inserts like this in steel as well. The only downside to them is, of course, because they're so sharp and they have such a high top rake, they wear out quickly. But in a hobby shop, that doesn't matter because we're not making that many cuts. You got to remember that insert tooling is designed for a production environment. You know, they're trying to balance a lot of competing goals. They're trying to balance chip load and production speed and tool life and all these different competing things that don't always play well together, whereas here in the hobby shop, all we care about is as sharp as possible, the nicest finish possible, and things like chip load and tool life really don't matter very much to us. For the second cut on each axis on this part, I need to remove a fair amount of material, and actually you can see I'm taking a pretty heavy cut here. This is a 50 thou depth of cut, which on a cut this wide is pretty impressive on a small machine tool. Nothing like a brand new insert. You gotta love it. In case it isn't obvious what I'm actually doing here, it's effectively a stock squaring operation, which you've seen me do lots. I've done entire videos on it. I'm bringing all four sides of this down to dimension while maintaining squareness as I go. I'm looking for 997 on this axis, and survey says, woof, look at that, 997. So that's the exact top of the tolerance for this axle box because it needs to slide right into the frame like this. And that slides freely, but there's no play. Beautiful. Then one more set of cuts to bring the other axis down to dimension. Once that's all done, then I square up the ends and bring it down to overall length. I decided to do this with side milling, which was a bit of an experiment. Didn't know if this was going to work. This is a lot of material to side mill. And in fact, this is right at the flute length limit of all of my end mills. I don't have anything taller than this, but I did just get away with it. The risk here is end mill deflection, so to counteract that, after each cut I do a climb milling spring pass on the way back, and that will do a little bit of extra cutting and take out any deflection that might have been especially at the bottom of that cut due to quill and end mill deflection. Then I flipped that around and did the same to the other end to bring it down to dimension. For the 5 of you that are actually following along with the book, you might notice my order of operations for this is quite a bit different than Kozo's. Kozo has various ways of doing things that tend to depend on the tools he has and the machines that he has, and I've got different tools and different machines, so I will differ in some regards with the way I think is easiest to do something. This block now is the correct outer dimension on all 3 axes for the final axle box. Now I'm going to center up with my edge finder because I've got a bunch of features that we can do from this setup. I need a shoulder cut into each end, and these are for the bearing caps. This is going to get interesting here pretty fast because we have to insert some bearing caps and then do a whole bunch of compound features that involve both the bearing caps and the axle box. And yes, I know the parallel is crooked in this setup. It's not enough to cause a problem. Don't worry yourself about it, but if you were thinking about commenting on that instead, use that energy to come and join my pointless internet pedantry club. We call ourselves the Well Actuallys, and everybody hates us. After establishing the depth on this cut, then I did some side milling over to get to the final width. And this exact same feature exists on both sides. I did my best to get it as identical as possible on both sides, which will become important here in a moment, as you'll see. While in this setup, I can also drill the mounting holes for the bearing caps for each. Now, you would think it might actually make more sense to make the bearing caps first and put them in place and then match drill all of these holes. And yes, that does make a lot of sense. However, what I've found over the years, honestly, is that if you do these bolt patterns carefully with the DRO and with good technique, they line up every time. So DRO for the win saves me time on setups. Next up, I've got this little piece of material for the bearing caps. I'm going to make both caps together in one setup since they both need to be the exact same size. So I'll machine this little chunk down to size to fit in those 2 shoulders. I'm actually going to leave these pieces a little bit oversized, and then I'm going to machine them down to match the actual axle box itself at the end. With the outer dimensions established, then I squared up the ends. Then I carefully cut these pieces apart on the bandsaw right down the middle, and then square up the remaining exposed ends, again leaving myself just enough material to make them oversize in all 3 dimensions. You can also see I've written the dimensions on the blocks, and when you're working with parts like this that are rectangular and very slightly different dimensions on the 2 axes, it's very easy to mix them up, and I have made that mistake, so now I just write the dimensions on things. I've got them both set up in the vise at once now to do the bolt patterns, and I'm edge finding on one using the absolute scale on the DRO, and I use the incremental scale for the other one. Of course, they both have the same y-axis anyway. This allows me to do all 8 holes in a single setup. You got to be a little careful doing this though. Anytime you put multiple parts in a vise like this, both parts will not get the same amount of clamping. Even though these 2 pieces are ostensibly identical because they were machined in a single setup, physics laughs at what we think is ostensible. If you want to be sure, it's a good idea to put a little piece of paper behind both pieces, and that will absorb any small differences and ensure that they both get equal clamping. In this case, I'm just drilling some tiny holes. There's not a lot of machining force on these parts, so we can get away with doing it this way. All those holes get countersunk now. These screws are actually just going to be fixturing screws at first for the subsequent machining operations, but they need to be countersunk so they won't interfere with setups, as you will see. Now I can bolt those blocks in place. The bolt patterns all line up perfectly because DRO, no match drilling required. Now again, I'm not throwing shade on match drilling. I do it myself all the time because it is a very good way to guarantee hole alignment of things. But just to show it's not always necessary, and in this case I think it saved me a couple of setups. So the 2 bearing caps are now bolted in place, or rather the blanks of them, and you can see that they're a little bit larger in every dimension than the axle box. So now I'm going to machine all those little sides down to match the existing surfaces. You might think it would be a little better to leave the entire assembly a little bit oversized and then machine everything down to final dimension all at once. And you're right, that would be a little better, and that was in fact my plan, and I got making the axle box and kind of forgot. But matching an existing surface like this is actually not as difficult as it might sound. It may look like I've cut into the axle box there, but I really haven't. What you're seeing is just a difference in luster caused by differing tool marks from the cutter touching the surface, but not cutting it. I know that sounds impossible, but it really does work. The secret is patience. When you're moving down to touch off on the surface you want to match, turn the fine feed on that quill basically as slow as you can stand to do so. like a couple of microns at a time until you just see the luster change as the flutes on that cutter start to touch that surface. If you do that, you absolutely can bring a surface down to match an existing one without cutting into the existing surface or altering its dimension in any way. It does take some practice, but you can do it. You do, of course, end up with some, mottled looking tool marks when you're done, but these are functional parts. If you care about the surface finish in that regard, you can put the whole thing under a Scotch-Brite wheel or whatever and make it all matched. For side milling, that technique is a little trickier because you can't actually see the surface you're trying to match while the cutter is in there. So instead, I just take a very light cut and then pull back and check, and then take another light cut and pull back and check until I can see that I've got a cut that's just touching that lower surface that I want to match. And again, there's no material have been removed from that other surface. We're just changing the luster of the surface where the flutes are touching it. All that done now, I've got the axle box all whole once again, but now with the bearing caps in place. Look pretty good. Now we can start to add features to this whole assembly all at once because the features we have to do affect all three components. I told you this was going to get interesting. Over to the lathe for the trickiest feature of all. We need a bore right down the center of this thing, and it needs to land right on the split line of those bearing caps. And this bore needs to be round, on dimension, and as straight as possible. This is a very long part as well, so any small amount of error on one end is going to get magnified at the other, and our bore is going to be all cattywampus on the other side. To make sure that doesn't happen, what I need to do is two different alignments. I need to make sure the piece is straight in the chuck, which of course it won't be after throwing it in there by hand. So I run an indicator down the length of it and tap it nice and straight on one side. And then of course I have to rotate the piece 90 degrees and do the same thing on the other axis. Now once I've got it straight in the jaws, of course, then we need to get it concentric. And that's a whole different operation. This is a dialing in operation for square stock, just like you've seen me do in my 4-jaw chuck video in my lathe skills series, if you want to know how this is done. It's really just like dialing in round stock, except you do one axis of the part at a time, and you have to rotate the part back and forth to find the low spot before taking a reading, and then make your adjustments from there. So it's a little bit slower than round stock, but essentially the same process. Now, the catch is, after you get this thing all dialed in nice and carefully, you think you're done, right? Well, no, because dialing in the concentricity of the part has affected the straightness of the part in the jaws. So then we got to go back and check straightness, tap that back in again, but then of course straightening the part has once again messed up our concentricity. So then we got to go and dial it in concentrically again. And you got to go back and forth, sometimes 6, 7, 8 times until both are perfect. Now the trick is, each time an adjustment of one parameter messes up the other parameter a little less and a little less. And so you actually do close in on that perfect straightness and concentricity as you go. It's not as tail chasing as it sounds. Final eye chronometer check is never a bad idea. Sometimes your eye will see stuff that you missed with the indicators, and that looks really good. All right, let's make a hole. This is a little nerve-wracking. We've got a lot invested in this part, and this is a critical operation. This has to go well. I'm going to start with a center drill, which I want to land right on the split line of the bearing cap. This doesn't actually have to be perfect because we are going to finish this with a boring operation, which will correct any errors caused by this drilling, but we need to at least be close to start with, and that looks good. Now in comes the pilot drill. This is a very long, deep hole, so we have to do a lot of chip clearing as we go. So patience is the order of the day once again. If you look closely, you might see that drill is actually vibrating a little bit. You'll see it more obviously with the larger drill that comes next. This is likely because my center drill caught that split line of the bearing cap a little bit weird, so the center drill was very slightly off, which is causing my drills to be very slightly off. This is why when concentricity is really important, you have to use a boring bar. You can't rely on drills and reamers for that. Drills and reamers are very good, but little tiny errors like that can happen, and there's no way to correct them without a single point cutting tool. A little bit of wobble here is no big deal though, because all these drills are doing is bulk material removal. As long as the runout in the drill is less than the final depth of cut that we'll be doing to clean up the bore, then there's no problem. Here you can see the drill wobbling a little bit more obviously. The reason concentricity is important here is not because there's anything spinning. The bearings are going to sit in this axle box, and the axle is spinning in the bearings. However, the concentricity of this bore relative to the sides of the axle box sets the position of the axle in the frame. So we do want that to be as close to where it's supposed to be as possible. Now for the boring operation aforementioned. This is a very deep and not very large bore, and that's always a tricky operation to do. I've got my largest boring bar that will fit in the bore, and I've got it pulled out much, much farther than is advised for any boring bar, but there are still 2 set screws holding it, and this is a solid carbide boring bar, which I have done some truly antisocial things with carbide boring bars. They are really impressive. They can handle a lot more stick out than mild steel or tool steel boring bars. Plus I've got a good sharp insert on there, and this is brass, and I'm going to take light cuts. I'm going to do one more important thing to manage deflection with this crazy setup, as you'll see, but here we go with our first cut. It's looking good. The purpose of this first cut is again just to remove the concentricity from the drills. Once you've got a full cleanup cut, then I can take an initial measurement and calibrate my DRO, set the current diameter for the DRO, and then start working to dimension from there. After each cut, I'm moving the boring bar back to center before withdrawing it from the work. Because of the amount of stick out I've got, there's going to be a lot of deflection in that bar no matter how light of a cut I try to take. So if I pull the bar back out, it's going to spring back and it's going to cut a spiral groove in my surface and mess it up. Don't want to do that, so I'm always retracting the bar to center before pulling it out on every single cut. There's 2 different approaches you can take with boring bars to make sure you hit a dimension. Either always do a spring cut after each pass or never do a spring cut. As long as you keep doing it the same way before each measurement, you'll hit your dimension. What you don't want to do is take a regular cut, measure it, then take a regular cut and a spring pass before measuring again, because then you're measuring different cutting conditions, and that's how you miss dimensions when boring. I also tend to avoid spring passes when boring with insert boring bars because carbide doesn't like really light cuts as a rule, so you tend to get chatter if you try to do a light spring pass on the way back out, and I have absolutely ruined an otherwise perfect bore by getting greedy and thinking I'll do a spring cut on the way out and chattering up the surface, and well, now it's a mess. The drinking game word for this video is patience. Yeah, to do a tricky feature like this, you really got to be patient. Light cuts, slow feed, every cut's going to take a while, but just don't get in a hurry. Don't start trying to optimize and make it go faster. Just be patient. If you've got a speed and feed that's working well, roll with it and let it do its thing. That should be my last cut, so we'll see what the snap gauge has to say about it. See if I did my job right. We can always make the bearings to fit, but, you know, feels good to hit a dimension anyway. And survey says, ooh, yes, nailed it. Which is how you know that dimension wasn't actually that critical. A little deburring, then I octuple check that there's nothing else I need from this setup before tearing it down. I've got about 30 minutes invested in just dialing in this part. That was quite an exercise to get it perfect, and I really don't want to do it again. Patience and careful work pays off every time though. Look at that bore, that is beautiful. Right down the center line, right down the split line on those bearing caps. Beautiful surface finish in there, perfectly straight through the part. Really, that could not have gone better. I was nervous about that operation, let me tell you. Now I can get the bearing caps separated again for some distinct features. I have to clean out the screwdriver slots because, remember, these surfaces were machined after those screws were inserted. I didn't take much off, but I did take off about half of those screw heads. Fortunately, there's just enough meat in there that I could still get the screwdriver in and get those out of there. If I had stripped those screw heads, that would not have been a good day. Not sure what I would have done. Maybe super glue some pieces to them and try to fish them out that way. Not sure, but luckily all 8 of them did come out. Those are starting to look like bearing caps. We have a few more things to do yet, but the end is in sight. Over to the mill now with the bearing caps. I got to add a shoulder feature to each one. The outer ends of the entire axle box assembly is reduced in size to fit inside those openings in the frame rails. The axle box itself is larger and sits inside. Now, once I've cut those shoulders, then I need to fix up the countersinks. Of course, I just removed 2 of them, and these top ones are now too shallow because I removed some material. I lined up on one of those holes with a pin, Then I deepen those top 2 countersinks. And of course, now that I'm lined up on one hole, I know the spacing of the hole pattern, so I only have to line up one of the holes, use a DRO to locate the rest of them, and fix all of the countersinks on all the rest of them. A little bit of deburring required yet, but that is one finished bearing cap. And of course, all the same operations were done to the other one. Back to the axle box now. I talked about how there's a shoulder on both sides at the ends of the entire assembly, so I got to put a little shoulder on the underside of the axle box at each end. One more nifty feature I can do from this same setup, these little shallow holes are actually lubrication points. I'm making a little oil cup, and then there's a little passage that goes from these little counter bores down into the bearings. The drawing calls for an angled passage to get the oil roughly in the center area of the bearing. However, the drawing does not give an angle for this, unfortunately. It just shows the passage at an angle in the drawing. I measured the angle from the drawing with a protractor, and it looks like it's about 18 degrees, so that's what I'm going to do. The angle isn't critical as long as the oil hole comes out somewhere in the vicinity of the bearing. With steam engines, everything is covered with oil, water, or both, and everything mostly ends up where it's supposed to. That's a surprisingly nifty little feature though. You can see the oil cup on top, kind of a reservoir that helps you hit the spot, and then there's a little angled oil channel down into the bearings. That's important because without that, there'd really be no way to lubricate these bearings. It's going to be completely inside the chassis. There's now a cross hole that gets drilled and reamed through the side of the whole axle box, and this of course is for the pivot pins that form the suspension. This axle box is the suspension of this locomotive. Here's one of the cross members that I made earlier, and that's a really nice sliding fit on there. Spins freely, no rattle, no slop, perfect. The last feature is quite psychologically painful because I have a lot invested in all of these surfaces, and now I gotta basically remove all of them. I've got to cut a great big channel right down the center of this thing. The axle box is actually open bottomed. I'm not entirely sure why, maybe just because there's no reason to enclose it, and if it's enclosed then you might get debris caught inside there. Keeping it open bottom just allows it to sort of be self-cleaning, I guess. Not really sure, but for whatever reason, the axle box is open on the underside. I cut this all the way through straight down and then a little bit of side milling to widen it to final dimension. This dimension isn't critical. With that final feature cut though on the axle box, you can see really how complex the geometry on this part was. And when making it from a single piece, requires a lot of setups, a lot of tricky cuts. Quite a complex piece of geometry there. Now let's get it all back assembled and see how we did. The bearing caps can get bolted back into place. I haven't shown this a lot on this project, but I actually number punch all of these pieces so they all go back in the same orientation and the same side of everywhere all the time. In principle, everything's interchangeable, but in reality, things tend not to be. Getting it all assembled now took a couple of tries to figure out the order of operations here. Turns out you have to disassemble everything, slide the cross members onto the axle box, then remove the end caps on the undersides of the openings there. I don't know what those are called. And the whole assembly can now slide down into the axle box openings. Then you can bolt the cross members back in place. Then you can put those bottom caps back in place. There's really no other way to do this as far as I can tell, so it's a lot of putting in screws and removing screws to take all of this apart. It does move now, but I'm not getting full range of motion. A little bit of analysis revealed that I need to chamfer these corners, and this is actually in the drawing, I missed it. This is required for clearance at the ends of travel on the underside. The top of the opening of the axle box has a fillet in there, so those little chamfers make clearance for that, and now the axle box can sit all the way down on that surface. I also had to add some chamfers on these top corners because there was some interference there. The clearances here are all very tight, and actually remember my frame rails are a little bit thicker than they're supposed to be. But a few chamfers here and there, and now I've got full range of motion. You can see there's still a little bit of a gap underneath near those caps, and that I think is just wiggle room in the design in case some of your dimensions aren't perfect. When it's all the way down on the front side, the other side is limited upward by the opening in the axle box area. So everything is on dimension, and this is the correct amount of travel. The design just has a little bit of extra space built in at the bottom there. That might also be wiggle room for if you get debris in there, it doesn't limit suspension travel. There it is in its final home. Not much different from the last time you saw the chassis, I know. I know YouTube's all about the big transformations in every video. Well, here in the real world, things take how long they take. This was a complex part, but I think a really interesting one. I hope you enjoyed the process of watching it get made, and we finally got some running gear happening on this thing. Thank you very much for watching. Stay tuned for many more cool parts. Thanks to my patrons for making all of this content possible, and I will see you next time.